The inverse cotangent function, \cot minus $1. Welcome. In this subsection, we will be exploring the inverse of the cotangent function. However, before we dive into the inverse itself, it is essential that we first revisit the behavior of the original cotangent function. We need to do this to understand why a specific restriction on its domain is necessary before we can formally define and work with its inverse. Review of the cotangent function, \cot $. Now, let's move to slide 2 and review the cotangent function. As I mentioned in the previous slide, before we can define the inverse, we must first have a clear understanding of how the original function behaves. First, let's look at the definition. The cotangent function is defined as the ratio of the cosine function to the sine function. In other words, cotangent of x equals cosine of x divided by sine of x. Next, let's examine the domain and range. Starting with the domain, we must remember a fundamental rule of mathematics. We cannot divide by 0. Since the sine function is in the denominator, the cotangent function is undefined whenever sine of x equals 0. Therefore, the domain consists of all real numbers except for n pi, where n is any integer. As for the range, the output of the cotangent function can be any real number. This means the range extends from negative infinity to positive infinity, or more simply, it is the set of all real numbers. Understanding these properties is essential because, as we will discuss in the next slide, the fact that the function repeats its values across this domain is exactly why we need to apply a restriction to define its inverse. The need for domain restriction. Now that we have reviewed the general behavior of the cotangent function, we need to address a critical requirement for creating an inverse. For any function to have a well-defined inverse, it must be bijective, which is a mathematical way of saying it must be both one-to-one and onto. However, as we can see, the cotangent function is periodic with a period of pi. This means that the function's values repeat themselves every pi units. To illustrate this, look at the example provided. The cotangent of pi over 4 equals 1, and the cotangent of 5 pi over 4 also equals 1. Because multiple different inputs are producing the same output, the function is categorized as many-to-one rather than one-to-one. If we tried to invert this as it is, the inverse would not be a function because it wouldn't know which of the many possible angles to return. To resolve this and make the function bijective, we must restrict the domain to a single interval where the function takes on every possible value in its range exactly once. For the cotangent function, the standard restricted domain is the open interval from 0 to pi. Within this specific interval, the function is strictly decreasing and covers all values from positive infinity to negative infinity without any repetitions. By limiting ourselves to this window, we create the necessary conditions to define the inverse cotangent function, which we will explore in the next slide. Defining the inverse cotangent function, \cot minus $1. Now that we have established why we need to restrict the domain of the cotangent function to the interval between 0 and pi, we are finally in a position to define its inverse. By definition, if we have y equals cotangent of x, where x is restricted to the open interval from 0 to pi, then we can say that x equals the inverse cotangent of y. Let us now look at the domain and range of this inverse cotangent function, as these are crucial for solving the types of problems we will see in the next few slides. First, remember that the domain of an inverse function is always the range of the original function. Since we saw in our earlier review that the cotangent function can output any real number, the domain of the inverse cotangent function is the set of all real numbers. Similarly, the range of the inverse function is the restricted domain we chose for the original function. This means the range, which we refer to as the principal value branch of the inverse cotangent function, is the open interval from 0 to pi. Example: calculating a principal value. Now that we have established the definition and the principal value branch of the inverse cotangent function, let us apply this knowledge to a practical example. We will find the principal value of the inverse cotangent of negative square root of 3. To solve this, we will follow a systematic 4-step breakdown. First, let us set the expression equal to a variable to make it easier to manipulate. We will let y equal the inverse cotangent of negative square root of 3. In the second step, we rewrite this equation in terms of the standard cotangent function that we reviewed at the beginning of this lesson. This gives us cotangent of y equals negative square root of 3. Now we move to the third and most critical step. Identifying the angle y from our basic trigonometric values, we know that the cotangent of pi over 6 is positive square root of 3. However, since our current value is negative, we must look for the angle in the second quadrant, as we previously discussed that the principal range is restricted between 0 and pi. To find this angle, we calculate pi minus pi over 6, which equals 5 pi over 6. Therefore, y equals 5 pi over 6. Finally, in step 4, we must verify if this result falls within the principal value branch. Since 5 pi over 6 is indeed greater than 0 and less than pi, the value is valid. Consequently, our final answer is that the inverse cotangent of negative square root of 3 equals 5 pi over 6. Key takeaways. Now that we have worked through a practical example, let us summarize the key takeaways to ensure you have a solid grasp of the concept. First, recall our discussion on the nature of the original function. The original cotangent of x function is periodic, meaning it repeats its values and is therefore not one-to-one. Because of this, we must restrict its domain to the open interval from 0 to pi in order to define a valid inverse. Next, let's look at the properties of the inverse function itself. The domain of the inverse cotangent of x is the set of all real numbers. This means you can plug any real value into the inverse cotangent function. Correspondingly, the range, which we call the principal value branch of the inverse cotangent of x, is the open interval from 0 to pi. This is the region where our final answers must always lie. Finally, I want you to notice a subtle but important distinction. Unlike the inverse tangent function, the range of the inverse cotangent does not include the endpoints 0 or pi. It is strictly an open interval. Please keep these fundamental rules in mind, as they will be crucial in helping you avoid the common mistakes we will cover in the final slide. Common mistakes. Now that we have covered the definition and worked through a practical example, let's conclude this lesson by discussing some common pitfalls to ensure you avoid these mistakes in your exams. First, let's address a very frequent point of confusion regarding notation. It is common for students to assume that cot inverse of x is the same as cot x to the power of -1. Please be very careful here. Cot inverse of x refers specifically to the inverse function, which, as we have seen, allows us to find the angle. In contrast, cot x to the power of -1 refers to the reciprocal of the function. This is simply 1 divided by cot x, which is equivalent to the tangent of x. These two concepts are entirely different, so always check whether you are looking for an angle or a reciprocal. Secondly, let's talk about incorrect range selection. When calculating the inverse cotangent of a negative number, some students mistakenly provide an answer in the fourth quadrant, such as negative pi over 4. However, if you recall our discussion on the principal value branch in the previous slides, the range for the inverse cotangent function is strictly between 0 and pi. Therefore, for any negative input, your answer must be an angle in the second quadrant. Always ensure that your final result falls within the open interval from 0 to pi to guarantee that you have found the correct principal value.